Okay, and then as the other instrument will be BIFROST. So it's like MERC-X, it covers the Y, J, and H band, optimized for Y and J band in this case, and it would go to VLTI. So we just submitted the first part of the ISO application documents last month, and we'll seek full approval later in the year. So you heard already Danny BIFROST talk about the Asgard suite of instruments, and this Asgard will consist of the high-five Albert nullers that Danny talked about, and then a fringe tracker and a fiber injection module led by Mike Ireland and also Franz Martinash. And the BIFROST module here is really about the short wavelengths and optimizing for high spectral resolution up to 25,000. So here's an overview about the teams that are working on this and trying to make use of all the synergies on fringe tracking and beam control that we can do. So we're also hiring here at Exeter. So there's opportunities to join us if you're interested. And there are very nice spectral lines that we could target there. For instance, here is the helium-1, Paschen beta, and Paschen gamma line in the Y and J band. H band would also be covered at least at the 5,000 spectral resolution, and kind of complementing what the lines that you get with gravity in the K band. So optical design has two spectral arms, where one spectral arm is always recording at the low spectral resolution, and it's basically used to monitor the photometry and to see whether there are fringe drifts or fringe jumps that this can be accounted for. And then on the high spectral resolution arm, we then also recorded a high frame rate with a second APD detector, but can then make use of the data that is recorded on the low spectral resolution arm in order to recenter the fringes. So basically apply a phasor term or throw out frames that have fringe jumps in them, and therefore obtain a higher SNR by doing the coherent integration later on in the data processing instead of really integrating for a few minutes uninterruptedly. And we hope that this will really allow us to use these high spectral resolution modes also for fainter objects by having long integrations. In terms of science, here half of it looks similar to what I just talked about for MERC-X, because there are these synergies, and we can do the same science on both hemispheres. But because of the UTs in particular, there's also some additional science you can do with BIFROST, such as, for instance, off-axis observations, where, if I have a slide here, we could use the same techniques that is used by gravity for off-axis interferometry of exoplanets, and basically apply this approach in the Y, J, and H band. And the work, for instance, also of the gravity team here has really shown that combining these different bands really allows you much better to pin down the essential parameters like the CO ratio or the mass of the planets, and then also learn about the formation process from that based on the molecules you find in the atmosphere, and telling you where the planet formed with respect to various snow lines. So other science case I'm very excited about for BIFROST is also using this off-axis mode, but to point at protoplanets such as PDS-70 B and C, where you might remember this spectacular ALMA image showing here the dust in the circumplanetary disk, but with BIFROST high spectral resolution, you could go there after the Paschen lines in order to measure the kinematics of the circumplanetary disk. I think this has already been attempted by gravity in the bracket gamma line, what you see here in the model prediction, which is here, this plot, is that the lines towards shorter wavelengths have significantly higher equivalent width, and therefore a higher chance that you can detect this the line and the kinematical signature in the differential phases that can tell you about the kinematics of the circumplanetary disk. And of course, there's also a lot on accretion and ejection for all kind of object classes that you can address. For instance, in young stars, where you have here magnetospheric accretion or disk winds, and where you could do some of the work that we started with AMBER some time ago, which had a 12,000 spectral resolution mode, but can do this in more suitable short wavelengths spectral lines that provide higher SNR, and also at multiple line transitions. So, for instance, if you look at the model predictions for disk winds, you see that velocity field consists not on the one hand of the Keplerian motion, but then also the poloidal velocity field. And the further in you go, the steeper the angle of this poloidal velocity field should be. And if you have multiple spectral lines, you basically probe the velocity field at different radii and can then really constrain such complex model predictions. Yeah, so that's again a summary slide here for the science cases of BIFROST, and I look forward to your questions.
Thank you, Stefan. Do we have any questions? We've got a bit of time to cover some things. Online questions. I'm not following. Conrad has a question.
Yes, thank you, Stefan, for this nice presentation. I actually have two quick questions. So did I understand correctly that for the low resolution and the high resolution arms, you can actually point at different objects on the sky? So for this planet case you were mentioning, for example, what is the field of view of these different pointings, if that is my correct understanding? And what are the second question is, what are the expected limiting magnitudes?
The two spectral arms, they always point at the same object, right? So the idea of the two spectral arms is that the low spectral resolution arm allows you to monitor any the metrology, right? Essentially the OPD drifts as well as the photometry. And you use then that information and apply it to the data that is recorded on the high spectral resolution arm. This is not like with gravity, where you have the fringe tracker and the science combiner pointing to different objects. But this is a new approach to really monitor your observables so that you can then apply corrections to your high spectral resolution data and improve the SNR by applying these post-processing techniques. However, as mentioned, we plan for an off-axis mode, but that means that the fringe tracker, which will be Heimdall in our case, points off-axis to BIFROST.
Okay, thanks. So Heimdall was not on my radar. Okay, so that answers the first question. So that one would be go off-axis.
Mm-hmm. Yes, and for limited magnitudes, it will essentially be set by the fringe tracker, and I think we estimate 9.5 for the 80s as limited magnitude. With Heimdall a K-band, and also the injection is of course critical, right? That in J-band you have the Boulder fiber injection module that optimizes the injection of the light into the BIFROST fibers, and therefore we also try to optimize that and have the deformable mirror and a separate adaptive optic system on top of Gravity plus AO and Naomi.
Okay, thanks.
I think we have another question over there in the chat. Any thoughts on trying integrated chip like Pioneer or Gravity for Bifrost? That's from Narcy.
Yes, that's one of the ideas. So we're just in touch with a company that manufactures integrate optic chips, such as used in Pioneer or Gravity, and have them design a J-band integrate optic chip that would basically replace here this part of the Merck X kind of design. And later in the year, we'll then decide which of the two concepts looks more promising and select them.
Okay, well, I think we better move it along. Keep to our schedule. Let's thank Stefan again.